Good day everyone, I am Alan Gabriel Lariosa, a third-year mechanical engineering student from the University of Science and Technology of Southern Philippines. Today, join me in solving a problem under torsion. But first, let us define the concepts to be tackled in this video. Torsion. In the field of solid mechanics, torsion is the twisting of an object due to an applied torque. Torsion is expressed in either the Pascal, an SI unit for newtons per square meter, or in pounds per square inch. Torque. Torque is the tendency of a force to cause or change the rotational motion of a body. It is a twist or turning force on an object. Torque is expressed in Newton meters or foot-pound force. Shear stress and shear strain. Shear stress, often denoted by tau, is the component of stress coplanar with a material cross-section. It arises from the shear force, the component of the force, vector parallel to the material cross-section. Shear strains measure the relative parallel movement of one reference plane with respect to another. The symbol for shear strain is usually the lowercase Greek symbol gamma. Modulus of rigidity. In material science, shear modulus or modulus of rigidity, denoted by G, is a measure of the elastic shear stiffness of a material, and is defined as the ratio of shear stress to the shear strain. Angle of twist. The total angle of twist is defined as the angle through which a radial section of a body, as a wire or a shaft, deflects from its normal position when the body is subjected to torque. Now that we have defined each concept, let's move on to our problem. Problem 3.119. Knowing that T equals 800 Newton meters and that G equals 39 gigapascals, determine for each of the cold-rolled yellow brass bars shown the maximum shearing stress and the angle of twist of end B. First, we have figure A and its corresponding dimensions. These are our given. T equals 800 Newton meters, G equals 39 gigapascals or 39 times 10 to the power of 9 pascals, A equals 50 millimeters or 0.05 meters, B equals 50 millimeters or 0.05 meters, and lastly, L equals 400 millimeters or 0.4 meters. Second, we have figure B and also its corresponding dimensions. In here, our given are T equals 800 Newton meters, G equals 39 gigapascals or 39 times 10 to the power of 9 pascals, A equals 70 millimeters or 0.07 meters, B equals 35 millimeters or 0.035 meters, and lastly, L equals 400 millimeters or 0.4 meters. Let's calculate the maximum shearing stress of the cold-rolled yellow brass bar figure A. We also have here our given. First thing we need to do is to calculate the ratio of A and B. That is A divided by B. We have 0.05 meters divided by 0.05 meters, and that is equal to 1.0. We're going to use this value to find our corresponding coefficients for rectangular bars in torsion. Looking at the table, 1.0 has C1 equals 0.208 and C2 equals 0.1406. The formula for finding the maximum shearing stress is T all over C1 times A times B squared. Substituting the values, we get 30.76 megapascals. Therefore, the maximum shearing stress of the cold-rolled yellow brass bar figure A is 30.76 megapascals. Next to calculate is the maximum shearing stress of the cold-rolled yellow brass bar figure B. The ratio of A and B is 0.07 meters divided by 0.035 meters, that is equal to 2.0. Again, from the table, 2.0 has C1 equals 0.246 and C2 equals 0.229. Substituting the values to our formula, we get 37.92 megapascals. Therefore, the cold-rolled yellow brass bar figure B has a maximum shearing stress of 37.92 megapascals. Let's move forward to the second part of the problem. That is solving for the angle of twist of end B. Solving for figure A, C1 equals 0.208 and C2 equals 0.1406. The formula for calculating the angle of twist of NB is TL all over C2 AB cubed times G. Substituting the values, we get 9.34 times 10 to the negative 3 rad, or 0.535 degrees. Therefore, the angle of twist of NB for figure A is 0.535 degrees. For the angle of twist of NB for figure B, we have C1 equals 0.246 and C2 equals 0.229. Substituting the values to our formula, we get 11.938 times 10 to the negative 3 rad, or 0.684 degrees. Therefore, for the angle of twist of NB for figure B, it is 0.684 degrees. That is how we calculate the maximum shearing stress and the angle of twist of rectangular bars in torsion. I hope you have learned something today. Keep exploring. Thank you.